Okay, so it's about storm surge forecasting. So pretty different physics from what we have seen before. No chaotic systems, no inflation, but we have system noise. System noise representing the uncertainty of our physical system, and we have to deal with it. We have to identify it. So the problems are slightly different because of the physics. But I will show you also that physics made life easy for us to really be able to develop an operational system quite rapidly. I will explain that later. So partly we were just lucky that we were able to implement the methodology very rapidly into the automatic prediction line. One moment. Yeah, that's first. It's about decision making in data assimilation. So I also have some slides about decision making. At least explaining how this process works. Okay, this was one of the most severe storms we had in the last decade. It was December 5, a few years ago, and probably you know enough about the Netherlands that we are located a bit dangerously in the sense that part of the country is below sea level, and also the western part where most of the people live. So we are pretty careful with protecting the sea, protecting the country from flooding. Especially flooding from the sea is really dramatic because the amount of water in the sea is almost infinite. So immediately the whole country will be under a level of meters of water. So it's way more serious than a river flood. Okay, so this was a few years ago, and but some people like storms. But here you see what's happening if it might get dangerous. We have many storm surge barriers, small ones like these. So if things get dangerous, people are called, and there will be a whole army of Dutch people walking along the dike, seeing whether things are safe, and preparing this kind of barriers which will increase the height of the dikes at locations where it's not at the required level. So if things are getting dangerous, really the whole country is coming in action, usually in the middle of the night. That's the common practice, that storms are usually very severe evening and in the night. So that's fact of life. And of course, yeah, and another thing, we have also big ones. This is the biggest one. This is the Zandvoort barrier protecting Rotterdam. Rotterdam is also located more or less at sea level. So if storms will create water levels of 4 meters above sea level, then it's obvious that the whole city will be flooded. It's not just a little bit of water on the street, but really with meters of water. So that's Rotterdam, and therefore they built this storm surge barrier that has to be closed in dangerous cases. So you see these are 2 arms. I don't know whether you've ever been there, but these arms are more or less, I think, almost the same size as the Eiffel in Paris. Big constructions, and the complication here is that the construction has been designed such that it can only be closed when the currents in the water are not too strong. That means that it has to be those kind of 6-7 hours before the actual danger situation. Because that's that we have when the tide is low and the currents are small, then we can close it, and then we have to wait 6-7 hours to get the tide all the way. Okay, and then of course you have to know this beforehand, so you have to predict what's going on, and that is the key issue in this system. Okay, then this is the decision-making process where civil engineers and modelers and meteorological experts are working together, and then usually meet in the middle of the night. But this is our model, which is part of the whole process where they can reconstruct or see what's going on with the water together with the meteorological condition, so they weight everything and to make a decision. And if they alarm the country, then a lot of action will take place. Okay, before we start with thinking of data assimilation, that was 20 years ago, there was no data assimilation, or at least it was in the hands of these people. So they got information of the weather, they got information of the water behavior from a model, but there was no connection with the data. The data came in separately, and they weighted this information just with some expert judgment. Neural network, but then a real one. In your head. Very deep learning. So that's when we started to think of how the amount of information is increasing. We get more and more information real time available, so we need to insert this in our models. Then first some experience with simple models, optimal interpolation, very simple, completely out of the question. I come back to that later if I show what models. Okay, so this is typically what had happened in this serious case of December 5. So this is what would happen if there is no storm. So life is quiet, and you just have the tide going up and down, very regular. We can predict this process of the tide over easily 20, 30 years in advance. So it's very depending on the moon and the sun. This is what the model is doing. So we have a numerical model, I'll show you later. It's driven by the meteorological input from our Royal Met Office, and it gives quite a reasonable prediction of what's going on, but no data there. So the next step is, of course, to use data to improve this prediction. That's the idea of data assimilation. And this is the real case of one of the most severe storms over the last decade. And here, I hope you can see it. This is what we do when we include the common filter. And you see the level is kind of 30 centimeters higher than the model predicted. So this is the moment that the decision had to be made. So okay, action was needed. And then of course, always to check whether what happens if you wait until the data is there. That made life here pretty similar to weather forecasting. If you make a mistake, it's a few hours later they already know this, and so it's pretty exciting to do, because if the prediction is wrong, then we are in trouble. But in this case, we see it was very good. You see the reds, the blue of the green one was the original one, the common filter prediction, and this was after all the realization. So it was pretty good. And we have, of course, this is running already for many years, so we have quite some statistic. So this is one case, but we have a whole bunch of predictions. Okay, now more what we are doing. This was more the decision process. Now we look to the model. Okay, we look to tidal modeling, and we can do that with the 2D shallow water equations. So we can use vertical integrated equations. You know the physics of shallow water, and if the wavelength is way larger than the depth of the water, then you can use a vertical integrated 2D model. Well, the wavelength of tides are 1,000 kilometers, so even in the deepest part of the Pacific, you can still use the shallow water equation. So that makes life easy. So we have the 2D grid. Oh, it's the wrong grid. Yeah, so this what I showed before. This is the model that's now in use. 20 years ago it was much smaller. So this process is continually going on. The model becomes more accurate, larger size, more accurately calibrated. So the model is not the same as 10 years ago. Every year they improve it. We help to improve so it's a live system that is alive. Okay, and well, to show the dynamics. Let me see. This is the model, but what I like to see is we have made some optimization, so you know to see the physics of the system. So you see tidal waves coming from the ocean, running along the coast and going back in this direction, and it is like yeah.
What does that mean? Please that you had something called active points. I don't know what's active points.
Oh, active points. That's the points that are moving. So you define a grid, but on land is non-active. So the real.
The parameter is I guess.
Yeah. Forecast. And that's done with common filter algorithms. Okay, model is formulated in a state-space form. So this is these are the shallow water equations, and this is the noise force, and that's different from atmospheric data estimation. These the weather prediction. We don't have a chaotic system. We don't need inflation, but this is the key point in our system. We have to model the uncertainty. That's really also a problem, because basically uncertainties are things that we do not know. If we know a lot about where the errors of the model comes from, then it's often useful or possible to improve the model. So it's a kind of complicated component. So this is the key thing. And then we have data, and we want to merge the data together onto an estimate. I usually have this linear operator because in our systems, what we measure is always the water level at a certain location. So the measurement operator is a very simple one. It contains a lot of zeros and a few ones. In case of satellite information, then things are different. Okay, so then it's what is the model uncertainty? If we have small models, then there are two, but if we have a large domain, then the main uncertainty is the meteorological forcing. The wind input in our system. So, nice, we blame, in fact, our colleagues from our meteorological office that they make the errors, but in practice, this is really the case. Open boundary conditions is also, in principle, more important error, but we remove the boundary condition as far as possible from our coast because of the domain that we have chosen. So basically by making the model larger in terms of the domain covered, we don't feel it really. Yeah?
That is the boundary conditions did you use?
What did you say?
What boundary conditions did you use?
Yeah, okay, maybe I can go to the so this is the model, and of course boundary conditions, land, water is easy, so that's just no transport of water. Here we prescribe the water level, and that's of course we want to use the model for computing the water level, and then there we have to prescribe the water level. And the reason that we have located this far away is twofold. First, it's far away from the Netherlands. It's a wave equation, so if you make an error here, it takes quite a long time before you feel it.
Before it can propagate to the region of interest.
Yeah. So that's one reason. And the second one, this is deep water, and in deep water, the weather has less influence on the water level. The shallower the water, the more the meteorological forcing will create changes in the water level. So by putting it in the middle of the Atlantic, where the water level, the depth is something like 6 kilometers, then it's not so influenced by the weather, and then we can, from satellites, we can estimate
the water level at the moment.
Yeah. So we estimate periodic functions which are reasonable for the planet. So that's okay. Okay, now, so it's about the uncertainty. And that was the meteorological input. Now, what do? We have this system noise, and it represents errors in our wind input. So, with a lot of data, we make two random fields as uncertainty description for the u velocity and the v velocity. So that this is isotropic. So this is the correlation or the random field for one location and how the wind in u direction is correlated with this point. So it gives a kind of spatial random field for the uncertainty in the u fields. Here we do it in the v velocity. And of course the parameters of this spatial covariance function are estimated by many cases, so it's tuned pretty well because we have quite a lot of data to do it. But of course this is still pretty simple. So, but this was the first idea, but this is the weakest point of the whole. With this simple statistics, we have to describe the variability of the ecological input in our model. So reality is way more complicated. Okay, and now so now looking more at the physics. We have shallow water equations, and for tidal modeling, the equations are weakly nonlinear, almost linear. Only in coastal areas where it's shallow, there we have nonlinear effects. So that is our luck, because that makes it possible to do an approximation, which makes life very easy, and also avoids all kinds of complications. So it's one serious restriction. So what we do is we explode the fact that the system is weakly nonlinear. And if it's weakly nonlinear, you apply the Assimilation filter, then you observe that the common gain is very slowly varying and it's almost constant. And that's the approximation that we use. We assume it's time invariant. And this is in this case, a pretty accurate representation. We compared it, of course, and then the partly is less accurate. Only on a very long scale with many data, you can see that there is a small effect with using the full time variant. And you can imagine this is really, we were very lucky. It was 20 years ago. Computers were not so big. If we came with this idea, this was really making it possible for very quick implementation in the whole data assimilation scheme. Because it makes that all the computations have to be done offline. Yeah, easy. You can use the computers to compute the steady state common filter. Localization is not an issue because if you average the common gain over time, it's simply more common gains to average. So it's relatively easy to get rid of spurious correlation that you cannot expect. So this made it possible to really include this common gain in the operational cycle. The additional computational effort is almost nothing. And time constraints are very strict. There's a 6-hour period in the automatic prediction line, so the first 3 hours are completely devoted to running the atmospheric model and to the weather forecast. Then the weather predictions are transferred to the shallow water model, which is run and gives prediction, and then the assimilation in the shallow water model is done to improve the predictions. And then we're almost at the start of the next cycle. So we had only 10 minutes for the escalation, otherwise we would not be able to do it. So this was very useful. Okay, but I said already the weak point is not that we use steady state filters. It's tiny little how do you say it makes the prediction a little bit less accurate. That's not really an issue. And also very close to areas where nonlinear effects are more important, and use this system as a system to provide boundary condition for local models where more accurate physics is included. So the fact that we use a steady state approximation is not really an issue, but this is an issue that even if the Conal filter is optimal, it's optimal given our simple representation of the noise input. So we try to see whether we can find ways to get rid of this simple system noise description model uncertainty. Okay. First one is, we could also see whether ensemble prediction systems are getting more and more popular. They provide a whole bunch of ensembles. So why not feed immediately the ensembles coming from the meteorological model into our color level system. But so that we try that, and then it turns out to be that it was even less accurate than our original statistics. So apparently the ensembles created in one meteorological institute is not really an accurate representation of the uncertainty in the weather forecast. Okay, so we found out very indirectly, of course. So we just saw it from our model level forecast that the uncertainty was provided by the ensemble was provided by the meteorological model is less accurate than what we had with tuning of our system. Okay, so then we thought of something else, and that's I think we want to use different meteorological predictions of different institutes. So we started a cooperation with our colleagues from the UK, and we use both predictions of our own meteorological office and the prediction of the UK Met Office, and we generated two predictions, one forced by one prediction and the others by the others. So we have two different meteorological inputs and it is two different predictions. Okay, now, what can we do with it? We come up with an ensemble Conal filter with only two samples, because we have two samples coming from very different meteorological inputs. The idea is two samples is enough to compute the full statistics, but not at one moment. You have to average over time. So what you do is, instead of having a number of samples and get the statistics from one ensemble, say 100 ensemble members, we average over time to get the statistics. And this completely eliminates the specification of model error, because the model error is provided by the two different models that we use as it. Okay, so the theory behind this is for time series analysis. So you need to assume that the process is periodic. So time averaging is giving the same results as ensemble averaging. And then if you have the difference, that's the quantity that we have, then we see that the expectation is the uncertainty of the difference. Okay, how can you use it? You can use it like this. We want to estimate the covariance matrix, which is in this case a huge matrix based on the difference between the two methodological inputs as provided by the methodological institutes. So this is the idea that you replace the classical ensemble average based on a whole bunch of ensembles by a time average, and in the time invariant case, or if this is a constant, it will give the same answer, but in a very different way. Okay, how does it look if you look at the algorithm? Because you need some iteration to get the answer. So what you do is first you assume that you have no measurements at all, and from the raw predictions of the methodological institutes, you compute the covariance matrix and use that in a kind of ensemble type algorithm to update the two ensembles. But of course that's not accurate, because you use over the whole time interval the model uncertainty without having included data. So that's never accurate, because in the real Connell filter you would have the recursive algorithm, so the next time step is already more accurate than the case without any data. So therefore you need to iterate. So this is a kind of first guess, and then it comes up with a new reconstruction. So here you start with the mean and the uncertainty as provided by the methodological institutes. They give us the two tracks representing uncertainties of the model. Then we can compute the common gain, and then if we have the common gain, we can redo the experiment and update the state, and the difference between the updated state and the realization that we have is the next iteration. And then you can repeat it. So the common gain becomes step by step more accurate. So it's an iterative algorithm over the whole time horizon. First a rough start, and then you go back with the more accurate common gain. Again, you get the data involved, you get new estimates of the states using the data, and then the difference that we observe is the mean trajectory of the two ensembles representing uncertainty in the estimate. Okay. Maybe Yeah, and in the linear framework, you can do, makes life easy, you can do some analysis. So the algorithm converges to a steady state filter, always for infinite length time interval. It also converges to the exact steady state filter of the gamma filter. And in the iteration process, it's a monotonic iteration process. So the filter gets better and better and better, and in terms of minimum variance filter, so the trace of the covariance matrix drops every iteration, and then at the end you have the optimal steady state. Okay, so let's see how this works. So this usually iterations are you need 5 iterations, same as in the reservoir case there. What you see is that this is the open loop, so that's this is the original model having no data included. Then it's the open loop, which means that you apply the covariance matrix without having included data as the model uncertainty. So it means that the model, in reality, the model will be more accurate, or the uncertainty is smaller. So the first step, you usually see that the drop is too large, so it goes too fast, too close to the data. And that's what you see here. It's too close to the data. But it's not optimal, of course, because optimality is related to the trace of the covariance matrix of the whole system. So it's realizing that it's not optimal, so the next iteration is getting better. And here we could easily even find the exact solution of the steady state filter. So it's really converging quite reasonable. This is the assimilation iteration, and this is the validation. So locations that have not been used to compute this common gain. And here you don't see this drop on the first iteration. So here you see the more regular convergence to a constant. Okay, so this is at least here it's it works. It's pretty efficient. So 5 or 6 iteration, and you have only 2 ensembles, so it's rather efficient. Although efficiency is not the issue, because everything is done offline. So if it would not be efficient, you just buy a big computer. So that's efficiency is not the issue as long as we can handle steady state systems. Now this is typically a model error now as computed by the system, so no assumptions, just reconstructed from a lot of data from the 2 different methodological institutes. So you see it's way more complicated. Correlation is also there, because in our statistics we issue independence of the velocity in y and v direction, but here I haven't showed a picture, but there's also correlation. So it's way more complicated. And then you see some far away things that we not completely because we haven't used localization. Principle, we don't need it if our time horizontal is infinite, so but of course we use finite samples, and then we still have some doubt about some things, so we could add localization to get rid of this. But okay, the final test, of course, is using it. That's of course, and so we used it for a year. So they call that semi-operational. So you have the operation system, and then exactly in the same production line, you have kind of parallel new version to really see what the new system is doing. So that's a kind of ultimate test where we have a year of statistics, and then this is what we get is show the overall statistics of this. This is the real what the managers want to see, especially this number. So this is the prediction horizon. This is if you just use a model and forget about data assimilation, and then our experts are doing clever things to include the data. And this is what the data assimilation improves. And you see here the difference between the old system and the new system based on the difference between the UK methods and our own methodological input. So it drops a little bit more. What you also see is that on the long run, the model is okay. And that is because of physics. We have a wave system, so improving an initial condition will only help you as long as the waves are still in the domain, so the wave will travel. In this case, more or less 12 hours, and then the wave is already in the area of deadlock, or it's not really relevant for our order level prediction. So then the improvement of the initial condition is gone. But fortunately, we are of course interested in this area where short-term prediction. Other thing is that here you see this effect. This is again the localization effect we believe. So this is what we need to improve. So, what I said. Here you see some nasty things. There is no data, so here are the data points, but the assimilation scheme will extrapolate a kind of correction in the remote parts of the model. And once they are here, it takes time to travel to the Netherlands. So this is kind of 12 or 18 hours traveling time. So kind of rubbish what we create here, or uncertainties here, will be visible in the prediction 18 hours later. So probably we will have to add localization here. That's this exactly 18 hours. If we kill these perturbations there, then probably this will be better. Okay, but the results are fine. Okay, so this was prediction. So we had parameter estimation. I didn't tell anything about that. That was already 3 days ago. We had the filtering problem. That's the next step. If you do an expectation maximization algorithm, you can do both state as well as parameters together. And we have the ingredients already there, so we can merge the two easily. And we can basically solve the full reconstraint for the part. So these algorithms are, in the loop you have a Kalman filter running, using the data to get the state estimate, and then out of the loop you have a parameter estimation algorithm which minimizes the innovation of the. This is a well-known technique in statistics, and since we have both ingredients, we can use it easily to compute the full reconstraint assimilation problem. And the reason that we can do it computationally is because the Kalman filter is a cheap, steady state. So computational effort for one Kalman filter simulation is just the same as one model simulation. So then it's easy to embed the whole system in parameter estimation. Okay, but it did not show any improvement. That's, we thought, great, we can do something that's very hard to obtain, but then it turns out it did not help. The good news is that therefore we can separate them. So estimating the parameters separately from the filtering problem is apparently a good way to do, because merging doesn't help. And also merging is also, it's not only that the results are not more accurate, but also you have an ensemble filter, it's the inner part of an expectation maximization algorithm. When you, in fact, you make the optimization problem less smooth. You have a kind of small scale wiggles that makes more complicated to solve. If you use an ordinary Kalman filter, it's the other way around. Usually you make your optimization problem in the output more smooth and more easy to solve. So, but that's a technical complication that we observed. Okay. So what are we doing now? So this is really doing well. But of course we are never done. We now go to the full ocean. We just get bigger. So this is a model what has already been developed. You see, this is the first model that we did 20 years ago, and this is the latest model. This is not operational yet. It will take a few years because this model is operation. This avoids also the open boundary condition because you just cover the world in your model. Still, shallow water equations are fine. If you want to compute tides, tsunamis, they all are fit in the framework of shallow water equations. The length of the phenomena is much larger than the depth of the water. So once we have the model, we need to calibrate it, and then of course we try to use all the data that's available to also assimilate the whole blow effect. I mentioned that these models are not ocean circulation models where we try to follow the dynamics of the ocean. This is just the wave on top, and the wave on top is propagating more or less in a linear way over the whole Earth. So this is a different problem, and we focus on trying to get the global system for the entire prediction using both the data as well as the model. Okay. There are a whole bunch of challenges here because I think the calibration problem is not so difficult. It's larger, but what's more important is to get the assimilation problem running, but because it's not obvious that this will be a steady state filter approximation. I think that we need probably time varying computations to get this running, and that will increase the computation orders of magnitude. So this is still work in progress, and that will take some time. Okay, that was what I would like to say as an example of a system with data assimilation, which is plays a role as making decisions.
Okay, thank you very much.
At some point, you said that I think that was in the slide 17. It was the point where you said that the Kalman game was steady, and that you assume that it doesn't change.
Yeah.
That was in operational data simulation.
Yeah.
I mean, how good is that? I mean, the Kalman game, yes, it tends to converge at some point, but in operational data simulation, the model is so complicated. It depends on so many observations that how good is to assume that the Kalman game does not change.
Yeah. Yeah. So in the let's.
I can understand that assuming that can ease the computation. Of course, if you don't need to calculate the Kalman game over and over, it's good. Yeah. But that I think that could not be so good for the.
You mean if you insert data? Okay. Yeah. If you look to the Kalman filter, and if you have a linear model, then the Kalman gain is independent of the data. That's kind of result of the Kalman filter. So the computation of the covariance matrix and the Kalman gain is not depending on the actual data. So that means that in the operation system it doesn't change that there is data. The only thing that matters is that the uncertainty of the data. That's important to know. So the Kalman filter wants to know the uncertainty of the data, but doesn't want or doesn't need to know the actual realization of the measurement. That's a fundamental problem of linear Kalman filters. And since it is weakly non-linear, we can do this trick. So we assume that it is time invariant. So does it help?
Maybe I think maybe you also something slightly different. But if you have a linear system and a constant measurement system, which you have the same measurements in every update step, then the Kanban game will converge to a steady state solution, or steady state Kanban game. And that's what you are using here, because this is a very linear dynamics. It's the tides is linear and the stone surges is same. But in a weather forecasting system, you could also use this, or if you have a system where the measurements are changing every time and there are different locations, etc. But they are really exploiting all the good properties of the Kanban filter to have an exceptionally efficient system.
In that case, I was thinking, the Kanban game is like a trade-off between the observation and the model forecast. And if the Kanban game is constant, then maybe one can ask, we can study this matrix, this Kanban game, to acknowledge what parts of the model are better than others. Is that possible? Is that?
Yeah, well, the Kanban game is the waiting for the data, but you can reconstruct the noise, the system noise in the system, and then you can might see where the model is wrong, or we didn't explode that.
Thank you.
Yeah.
I wanted to ask a question. If I remember right, in the space state equations, in the nonlinear dynamics equation, there was a term, an error term, that term is accounting for more uncertainties, right?
Yeah.
And is there any assumption of the distribution, statistical distribution of this error term? Maybe Gaussian, normal, or can be whatever distribution you may not find.
Yeah, it's a Gaussian error, especially in the linear case we write Gaussian.
Right.
It's theoretically only the covariance matrix is relevant, so you can choose any distribution. But in practice, I think the Gaussian recipe
Or any works for
and it works. Yeah.
Thank you.
But yeah, there is a lot of tuning because
And because of the non-linearities, I guess. Thanks.
Yeah. Okay.
Questions for Professor Heemink? Other questions? Thank you very much.